we've talked about centripetal acceleration. That's the acceleration of an object that points toward the center of the circle. Because that velocity vector is continually tipping toward the center, there's an acceleration vector toward the center. What causes it? And the answer is the centripetal force. Define the centripetal force for uniform circular motion and state its direction. So the centripetal force, this is, some of you have heard of centrifugal force. That's something different, and we'll talk a little bit more about that later. But we're talking about centripetal force now. The centripetal force is the net force acting on an object in uniform circular motion. It points toward the center of the circle. It's center seeking again, toward the center, and it's in the same direction as the centripetal acceleration. You say, well, that makes sense, because Newton's second law says that the net force is equal to the mass times the acceleration. So that net force, darn well, better be parallel to the acceleration. And in this case, it is. All cases, it is. So let's do an example. Model airplane has a mass of 0.9 kilograms and moves in a constant speed. This is again another control line plane. Moves in a circle that is parallel to the ground. Find the tension in the 17-meter guideline for a speed of 19 meters per second. So we've got a speed of 19 meters per second. We've got a tension in this guideline is we're supposed to find it, find that tension. And the radius is 17 meters. So that's the radius. This is the speed, 19 meters per second is the speed. I want to try and find the tension. And we have to be careful because this T now does not refer to period, it refers to tension. Unfortunately, we run out of letters in the English alphabet to be able to do everything. But this represents tension. Let's write down Newton's second law. And the way that you go about it is you just follow the same steps that we talked about before for solving Newton's second law problems. We choose a coordinate system. And I've chosen this one with x, with the origin of coordinates at the location of the plane. And you say, well, hang on, when the plane moves over here, x is going to be the wrong direction. It won't be toward them. And I say, let's just look at the instant that this plane passes this origin of coordinates. And at that instant, I'm okay with that. So this is a key to solving uniform circular motion problems. If you choose the x direction to be at the location of the ball or whatever is going in a circle, the plane in this case, and you choose x pointing toward the center of the circle, then things work out pretty simply, as I'll show you now. So let's ask about the forces on this plane. Well, there's a tension force that's pulling it toward the center of the circle. And in fact, that tension force is the centripetal force. It's the force that's keeping this plane in circular motion around the man. What's the centripetal force that holds the Earth in orbit around the sun? You might say, well, gravity, right? And I say, yeah, it is. And we'll do examples with that later. So that's the centripetal force. Tension is the centripetal force. And if we look, and that's the only force in this x direction. So we'll plug this tension in for the net force in the x direction. And we put it in with a positive sign. And the reason is it's pointing, this is the direction of x. It's toward the center of the circle. This is the direction of t. It's toward the center of the circle. So the x component of the tension is positive. That's why we put it in as positive. And then we're also going to look at the acceleration on the right side of this equation. Mass comes along for the ride. Then the acceleration, we want to know what the acceleration is of this object. Well, we know that its velocity is changing. We know that it's accelerating. And so it's going to have an acceleration that points toward the center of the circle, and that happens to be in the same direction as x. So the x component of acceleration right here is equal to the magnitude of the acceleration, which is just v squared over r, which we've talked about in the last concept. And that's it. That gives you the tension. Plug the numbers in that we have, 0.9 kilograms, and that gives a 19 Newton tension. Now, some of you might have acquired a bad habit of looking at this in terms of a centrifugal force and thinking about this in a non-Newtonian reference frame. A centrifugal force is the force that you feel when you're in a car when it's going around a turn. And if you're turning to the left, your acceleration is toward the center, but you feel a force toward the outside. That's called a centrifugal force. But it's a force that's only felt when you're in a non-inertial reference frame. We're not going to use non-inertial reference frames. We're going to use the reference frames because Newton's laws are only valid in inertial reference frames. We're only going to use reference frames where we're standing on terra firma and we're not inside that airplane in that non-inertial reference frame. And from his point of view, the only force acting on that plane is that tension force. An unbanked turn. This is a great problem. We have a turn of radius 300 meters, and the coefficient of static friction between the rubber and the dry road is 1.0. So this goes back to chapter 4. Great example. What's the maximum speed at which a car can complete the turn? Well, how are we going to set it up? We're going to write down Newton's second law, do it in the x direction. And in the x direction, there's one force acting on that car in the x direction. It's the force that turns the car. It's not like we talked about in the introduction a couple chapters ago, it's not the steering wheel that turns the car. The steering wheel turns the wheels. The wheels are in contact with the pavement. If there were no friction between the wheels and the pavement, when you turn the wheel on the car would still keep going in the same direction. You'd just be sliding right along. It's friction that turns your car. So we've got this static frictional force. Since the tires are not sliding, they're gripping the pavement, or at least you hope they are not sliding. And we've got a static frictional force that is responsible for turning the car. So the maximum static connection, we're asking what's the maximum speed that the car can complete the turn at. The maximum refers to if I keep going faster and faster and faster, how fast can I go before the car starts sliding? And so that's what I'm talking about here. It's just at the point where the car would start sliding. Equals, the mass comes along for the ride. The acceleration, just like in the last example, is v squared over r. We're also going to have to look at the forces in the y direction in this case. The y direction is vertical, so the x direction is toward the center. So in the y direction, we need to try and figure out what those forces are. Well, there are two forces. There's the force that stops the car from falling through the road. That's called the normal force. And then there's gravity, just the weight of the car. Just those two forces in the vertical direction. Well, the y direction we're taking to be vertically upward. The normal force is in that same direction, so we put it in with a plus sign. But the weight of the car is pointing in the minus y direction, so we put it in with a negative sign. And then we're claiming that on the right-hand side, this acceleration in the y direction equals 0. And you say, well, hang on, isn't gravity, right? It should be 9.8. Well, that's only if it's in free flight. It's not in free flight. It's being held up by the road. That velocity in the y direction is not changing. Why is that? Well, the velocity of this car in the vertical direction is 0. The component of velocity in the y direction equals 0. So it can't possibly be changing because it's 0 now and it'll be 0 later. So there's no acceleration in the y direction. A very important point. So that's why we have a 0 right here. It's not accelerating in the y direction, only in the x direction. The other way that you can know that, and it's nice to be able to come at this from different directions, is that this car is going in uniform circular motion. We've already discussed the fact that if you're in uniform circular motion, then your acceleration is pointed toward the center of the circle. End of story. I don't care what kind of direction of the circle is in. If it's in uniform circular motion, the acceleration is toward the center of the circle. And that's the x direction and not the y direction. Perfect. So now we can put everything together because there's an equation from chapter 4, I forget which concept it is, that says that the maximum static friction force is equal to the coefficient of coefficient of static friction times the magnitude of the normal force. And it's one of the very last concepts in chapter 4. Fs max, we already know from this equation. So instead of Fs max, we put mv squared over r for the left side of this equation. And then we know Fn, we can solve that from this equation. Add mg to both sides, and we get Fn equals mg. And we plug that in for Fn here, Fn equals mg. And we are pretty much done, because notice how amazing our life gets at this point. The masses cancel on either side of the equation. Multiply both sides by r to cancel out the r's. I'm sorry, the r stayed here. These two r's cancel. Multiply both sides by r. These r's cancel. We got v squared equals mu s r times g. But I want to solve for v. So I take the square root. So v is mu s r g. And you might say, well, that's a lot, that's a mouthful. But we'll give you some opportunities to practice this in the homework. How are you going to attack these kinds of problems that involve circular motion and forces? In this case, a centripetal force, is you're going to write down Newton's second law in the x direction, pointing toward the center of the circle, the radially inward direction. You're going to apply Newton's second law to the direction perpendicular, and then you're going to relate, usually there'd be some maximum that you can relate to the normal force, and then solve. And what is, in this case, the centripetal force? In the case we talked about before with the plane going around in a circle, it was the tension. In the case of the Earth moving around the sun, it was the gravity. What's this centripetal force here? And you say, is it static friction? And I say, yes, it is. It's static friction that provides the centripetal force to match up with the acceleration. Here's another example. The rotor is a cylinder of radius 2.85 meters, whose, and the vertical direction is upward like this. That's up. And whose floor lowers when the rotation speed reaches 33.3 RPMs. And I might just have a video show how this works. So some of you might have ridden on amusement park rides like this, and I have, and they're pretty cool. So what's the physics of them? Well, the answer is, and what we're trying to do is to find the centripetal acceleration and the minimum coefficient of static friction needed to prevent riders from sliding down the wall. If you've ever been on a ride like this, first of all, you're standing on the floor, then they spin up the rotor, and then the floor drops away, and what you feel is your body has a tendency to slide down, and your clothes are getting hiked up on you, but your clothes and you feel like you're stuck to the wall. And so let's first of all, we're told it's 33.3 RPMs, which is revolutions per minute. And let's convert that to revolutions per second. We've done that before. Just convert seconds to minutes. The period is 1 over the frequency, and that's 1.8 seconds per revolution, or 1.8 seconds. And what is that? That's the time for one complete revolution. Then the speed that this person is going, we can find from 2 pi r over t. We did an example like that previously as well. Plug the numbers in, we get 9.8 meters per second. It just so happens to look like 9.8 meters per second squared, but it is a speed, and 9.8 meters per second. Then the acceleration is v squared over r. We just found the speed. We know what r is. That's 2.85 meters. We can plug in and find the acceleration, called the, what kind of acceleration? Centripetal acceleration. Perfect. And then we're going to use those same the same procedures that we did in the previous case with the static friction force. First of all, could you tell me what the centripetal force is in this particular case? Well, let's look at the forces on the man. We've got gravity pulling him down, no doubt about that. We've got something holding him up that's preventing him from sliding down the wall. What is that? And you say, well, isn't that static friction? And I say, yeah, sure is. It's holding him up. So what's pushing on him this way, toward the center of the circle? And the answer is the normal force. So which of these three is the center-seeking force, the one that points toward the center of the circle? You say, well, isn't it the normal force? And I say, yes, it surely is. The normal force is the centripetal force in this particular case. If we take, as we have done before, x toward the center of the circle, y vertically, then, and we do Newton's second law in the radially inward direction, in the vertical direction, and then put everything together, we follow the same procedure as before. There's only one force pointing toward the center of the circle in the x direction. That's that normal force. The centripetal force is the mass times the acceleration, which is we've already calculated. So we don't have to put v squared over r here because we already worked out what the value of that is. What about the vertical direction? Well, there's a static friction force that points up, so it's in the plus y direction. And we're interested in the maximum possible static friction force so that that will give us the minimum coefficient of friction enabling him to not slide down that wall. Gravity is acting in the minus, here's the y direction. Static friction force acts in the plus y direction, so it's positive. Gravity acts in the minus y direction, so it's negative. And the acceleration in the y direction is 0. And I ask you why. And the answer is that all of the acceleration is toward the center of the circle. It's uniform circular motion. So the only direction that the acceleration can point in is x, toward the center of the circle. There can't be any in the y direction. And Another way to think about it is that this static friction force exactly balances out the gravity, and you hope it does, otherwise you're going to slide down the wall. So this is the relationship from Chapter 4, that last concept, I think it was, in Chapter 4. Fs max is mu static times the normal force. Fs max, we can find from this equation, is equal to mg. So that's where that one comes from. Then mu-s comes along for the ride, down from here to there, times Fn. But Fn we can find from this equation, it's just ma. So here's my Fn, which is ma. The masses magically cancel, and we can solve this equation for mu-s by dividing both sides by a. The a's on this side cancel, and we get mu-s equals g over a. G, we know it's 9.8. A is 34 meters per second squared. So that's about 3.5 g's. It's a fair amount of acceleration needed to do that. And so mu-s has to be, at a minimum, 0.29. If it were less than that, there'd be less static friction and you would slide down the wall. If it were more, then that's fine. You still stick to the wall. To analyze a problem like this, let me just set up what the forces would be. And some of you have ridden in rides like this too. You've got a tension acting up in this direction, gravity acting down like that. And how would we set that one up? He's moving in uniform circular motion at a constant speed, and these are the only two forces that act on him. There's no centrifugal force. There's just the sum of the forces is the mass times acceleration. Sum of the forces in the x direction, mass times acceleration in the x direction. And let's take, as we always have done, x toward the center of the circle, y vertically, and look at the forces toward the center of that circle. This angle has to be 30 degrees if this one up here is 60 degrees. And the forces in the x direction, there's really only one. There's the x component of this tension. This is the tension up here that acts at an angle of 30 degrees. And I want its x component. So that's going to involve the cosine, t cosine of 30 degrees is mass times acceleration in the x direction. Well, the acceleration is in the x direction, and its magnitude is v squared over r. Then the other main equation is sum of forces in the y direction is mass times acceleration in the y direction. Well, what's that? We need to know what the forces are in the y direction. Well, there's a y component of this tension because it's acting at an angle. It has both an x component and a y component. And that y component will be t sine theta. And we also, and it comes in with a positive sign because the tension is pointing in the, not exactly in the plus y direction, but it's certainly not pointing away from y. It's pointing in the direction of y. So it's going to be positive. And then the gravity points in the negative y direction. And then equals the mass times acceleration in the y direction. This is the third example of this. What's the acceleration in the y direction? It's g, right? 9.8, right? Well, no, it's not. What is it? It's 0. And how do you know it's 0? Because this is in uniform circular motion. This is the acceleration. It's pointing toward the center of the circle. And this acceleration has no component in the y direction. It's only in the x direction. And the other way to think about it is that if there were acceleration in the y direction, then this guy would be going up higher. He'd be getting higher in the air instead of going in a horizontal circle. That's why the acceleration is 0. So these two equations will allow you to solve for anything you need to solve for, but that's how to set this problem up.